Hi everyone. Let's wait for 2 more minutes and let's get started. Yeah, we can start, I think. Yeah, so in the last webinar, we were learning about what is VLSI and what are the flow in the VLSI, like basically basics of VLSI and what is VLSI design flow and what is front-end flow and what is back-end flow and what are the fabrication techniques that are currently in the market and how the packing is done and also we were learned about how the career in the global and in the Indian market. Okay, so we'll go for each of the specific domain in the VLSI in today's webinar. Okay, so today's day two webinar will be covering about for how the RTL what are the RTL design people do and how the design verification people do the verification process and how the logic synthesis people do the synthesis and what the physical design people do and the next the fabrication how it is done and testing and production. So we'll go to the each of the topic in detail in this webinar. Okay. Yeah, we covered yesterday about how the design will start, right? So basically, right? So we will be having is an idea of basically what are the requirement? Is it for mobile or a laptop or a TV? So on that purpose, we'll start our requirement, right? Then we'll give a specifications required, whether it has to be having some 16 core or 8 core or 32 core with having some speed of 4 gigahertz. Okay, and this will be having a memory support up to a 1 TB memory and 128 GB of RAM. So all the specification will be defined for a processor. Okay, and any features and new features that will support how much the speed of the response that is required for each feature. So that all are comes under the specifications. Okay, coming to the specifications, we go to the design architecture team, right? So the design architecture team will start designing the particular modules, how to create for each of the features that is there in the specifications. So they will create the architectural level designs and they will give the module wise distribution for the RTL engineers. Okay, so the RTL team, basically the RTL team, this team will write out the RTL code that is in a VHDL code or a Verilog code. Basically, they will write this in a code format, the logic which is defined by the design architecture team, that is in the circuit forms, basically circuits, basically behavioral formats, which is like a full adder or a counters. So that all are converted into a logic level, like a gates. Then that gates are the format of a basic gates or a add or a subtractor, or what you can say is what is like what is the sequential circuit that will be defined in a flow formats. Okay, with that the RTL team will design the RTL code. Okay, once the RTL code is done, so we may have a lot of redundant code in our design, right? You can say like there are some a billion gates, but the space for the chip is only having a zero point 0.8 or a zero point 0.5 of billion, a 500 million. Okay, so we need to sync out that. We should not use the number of gates as many as we want, right? So we have to sync it them. So we have to logically, it has to work how the functionality is there, and also the design has to be properly verified. So this will be done at synthesis and the functional team, like a design verification team will verify this logic in to and fro process. Okay. Then after the logic synthesis done, the logic is optimized properly in terms of area, in terms of timing, in terms of power, basically the power usage for that particular chip. Then it is submitted to the physical design team. Okay. So then the physical design team will deploy all this in a CMOS structure or a transistor level. Okay. This will be created. All these transistor levels are created by the analog layout tools. They will give the each character of cell. Basically, if you have an AND gate that will be converted to CMOS level, that will be defined by the custom layout or analog layout teams. Okay. So once that is done, everything will be placed the proper way without any overlaps, without any shorts, without any spacing constraints. All this will be considered the physical design. Physical design is also plays a very big role in the layout. How the logic remains accurate, the same it has to be implemented in a physical format, in a layout format. Then it will be done. The report will be done, and the fabric. Then it is submitted to the fabrication units for the fabricate of the chips. Okay, this is how we covered about the what is VLSI in the last webinar. Okay. And coming to the next, what do you say? Next slide. This is about how the VLSI standard flow. Basically, we are talking about there is a flow, VLSI flow, but there is again the standard, what is actually done in terms of the front end and the back end. So once you go to the specification, the architecture will be designed, then the RTL code will be done, and the simulations will be done, whether the inputs are working properly for the output. Then it is done for the synthesis. Okay, the synthesis stage, right, will be assigning each gate to a particular character or a standard cell. Let's take you have an imaginary gate, but that has to be physically has to be present in our chip, right? For that, the layout team will design a particular standard from the particular standard for that CMOS. Basically, they will create a CMOS for each of the MOSFET. Basically, a FinFET or a technology they use a GWA technology. What they use, they will convert into that particular standard cell format for each of the cell, and they will submit it to the backend team. So backend team. So here the backend team, they will do the timing analysis, how much the speed chip has to work, and how the data has to be ready for the each of the inputs they have required. And then the floor planning. The floor planning is process where they'll create uh, like planning for each of the RAMs or a unlock macros or a digital to unlock converters and PLLs. All this they will place in the right directions. Likewise, we'll cover up each of the step in detail in this backend. Okay. Let's go to the next step and we'll cover up each of the step in detail. Okay. So as we covered the specifications, when we say the frequency, when we say the area, we will be talking all about the speed and area and the speed and also the power utilization, right? The power, how much chip is consuming the power, right? So this is how the each and every chip will be calculated, how much the speed is working. If I say someone is calculating the how much the power is using by my chip, that how the sleek and the very thin laptops will come. Because the battery that we use are max will be 10,000 mAh for the laptops, okay, or 15,000 mAh. But in that 15,000 mAh, how much this battery life is giving for a particular chip, how much it is consuming. Okay, 90% of the battery consumption will be used by the chip only. The rest it will use for the display or a the mouse or a input and output interfaces like a keyboard and a speakers. But max power will be used by this keyboards. I mean the chips only. Okay. This is how the power, speed, and area comes. And in the industry terms, it is called as a PPE, power, performance, and area. So that how the chip quality will be tested once the chip is fabricated, how accurately they are working when it is fabricated. Okay. So this is how the specifications we define. And this architecture team, basically micro architecture team design. Like why it is called as a micro architecture is because all the design we design is in a like micro level only basically. Okay, that's why it is called the micro architecture designs. Okay, people have called in the different terms in the different companies, but this is the one of the way we define as the architecture team design. Okay, so any company that designs a specification given by the customer who is the customer basically the customer itself a users user requirement basically the HP they will be or a Lenovo company or any other Dell. So they have the specifications required for the market requirement. They will specify this much speed, this much power it has to use. Okay, they will decide. And on the market requirement, the companies like Intel, AMD, they will target basically that targets. They'll put the targets and they'll release again to the market. They supply to these customers. Okay, so they will be designing this architecture on on a logically using this logic gates. Basically they will be like any design. Let's take a small design where it is like calculating a time number. Let's take it will use around a 20 to 25 of gates, basic gates, and it has to design in a Verilog format. First, it has to define in a combinational circuit. So first, we need to create in a functionality is working correctly in a combinational circuit. Then we have to define it is in a synthesized way. Then we have to convert that into a Boolean algebra. Then we have to convert it to a Verilog code. So that is like a VHDL code. So that how the RTL code will be created. Just I'm taking a small example of a prime number calculator or a Fibonacci, like just an understanding purpose. Okay. So this is how the architecture is done. So next, the RTL design team will design the each and every what do you say required modules for each of the connectivity. Let's take I wanted to add every time some number, so that need a one adder here, right? So when you give an input of 1 1 1 1 three inputs, it has to give a output of how much? Three, right? That is a double one. So it's a two input, I mean three input and two input, three input and three output adder. Okay, this is how they will create the behavioral modules, then will be converted into gate levels, and the code is used for the Verilog. Okay, that will be written in a Verilog format and finally at RTL switch. Okay, and what is simulation? But everything is working fine. The logic is created. But what you giving, like all the combinations you give, is it working properly or not? That will be tested by the simulators. We have the CAD tools for simulators. Okay, with that simulators, we're creating a waveforms created in our designs, right? So the waveforms, like you are giving a adder, you're giving a one as an input, three inputs. Or let's take a two input adder. You are giving an input of one, and output should be 10, right? So that 10 is coming at output or not, it will be tested out by a waveforms. That are called the simulations, basically the simulators. Okay, we need to check functionally that are working correct or not. If functionality is verified, we need to go to process called synthesis. Okay, once this is like synthesized properly, once this is synthesized design, they again they'll go to a process called synthesis. Once this is verified, at synthesis we will be shrinking out the quality, like shrinking out the number of gates or number of transistor level count, and we'll be again writing that code into a Verilog format only. Okay, so try to just remember this naming conventions like Verilog, what the file formats we're using here. So we'll be covering up in the later slides. So coming to the synthesis, right? Site synthesis. So synthesis is basically a technology dependent design. Basically, what is technology dependent? You have a Verilog logic, but that logic will be assigned. Basically, you have a NAND gate. That NAND gate will be assigned to a technology file. So what is technology file? Basically, so technology file where a fabrication unit or a manufacturing unit, or you say, which will manufacture these chips finally after all this design process in the cathodes, is short copy, basically a GDS file. They will basically the fabrication units they will provide a technology file like a standard for each of the gates. A CMOS should be like this for a NOT gate, an AND gate, or adder, fladder, flops. So all this was mentioned in the technology file only. It is like a reference mapping. Basically, this NAND gate will be again same will be defined in technology file in a physical format. So that will be used by this synthesis to synthesize in a proper way. And different technologies are there. We have 32 nm, 45 nm, 50 nm, and we have a lower technologies like 10 nm, 5 nm, 2 nm. All these are like technologies. For particular chip, if you want a more performance, more speed, we are using a very latest technology. A chip from the automobiles doesn't require the latest technologies, I can say. They can just still the 45 nm. So same like that on requirement, they will use the different technologies. Okay. So once the synthesis is done, they will be giving a two different files. That is the main important two files are like Verilog file. Okay, that is .p. The second one is constraint file. What is constraint file? Okay, basically the constraint file having a input and output delays. Okay, again the clock periods are defined for each of the logic that we have in terms of flops or clock getters. Okay, and how much frequency that has to work, that we find in the this constraint clock period, input output delays, multi-cycle paths. For one path, basically the one flip flop, basically what is this, a setup time or a hold time, that is a timing calculation we call. We require a time for each one cycle, it has to store the one bit of data, right? So this however the timing period is calculated, all these are defined in this STCs. Okay, this how the STCs are required for any layout layout steps. Okay, from the synthesis to GDS, we require this STCs. I mean, not before this GDS. Okay, till the sign off stages. until chip is properly validated. Okay, so we have a different CAD tools for the synthesis. There is a no manual interaction with these billions of transistors. Back then, they was used to draw in a computers, but now it has become very flexible with the CAD tools, and the billions of transistors or gates are handled in hours of time now. Okay, the complexity is also that it peaks, I can say. Okay, this is about the synthesis. Okay, next about the design for testability. Okay, so what is DFT? Basically, we call it as a design for testability. It's like a DFT. So some people want a DFT only. So they are not interested in DFT because it is like testing your logic. Basically, testing out a logic is like you have a logic, prime number which will be giving a 3 as input, and it will say output of 1 if it is true. It will say 0 if the logic is the input you have given is like 4, then it's not a prime number, let's say. Then it will say 0. So like that, we having a like input and output at 0. But the connections which we have, there might be some connection lost between each of the when the input is like when the chip is manufactured. We don't know at which gate or at which block which is not working properly. For that, for each of the flow, okay, for each of the flop or a register, there is a testability whether that flop is working to store the data or not. If something is not storing properly, it will acknowledge and will decide on which data path it has to take care. So that's how the design for testability, whether the logic which you are giving is properly working in the later stages. Okay, so that's why the DFT is most important, the design for testability. So this logic is inserted. The connections will be created for each of the flop in the design. Whether that flop is storing properly the data or not. Then they will be testing out the post silicon process, like the post manufacturing process. Okay, and there are different softwares to test out this DFT. Okay, so and there are different patterns of for DFT testability. Okay, this is how the DFT is there, and coming to the inputs to the next stage of the backend. Okay, at backend stage, once you completed this print-end process, we have a logic. First, in the level RTL team will create the logic required in the VHDL format, and it is resynthesized. Okay, and for the synthesis data, will insert the DFT logic. That logic will required to be submitted for the backend design. So, what are the files required for that? Basically, for the backend team, the physical design starts. The layout team will start their work. Okay, we require a Verilog file. We require a constraint file, that is SDC. We have a scanf file, that ATPG file is a scanf file. Libs is called the timing libraries for each of the cell. There is a characterization, right? So that is like a feature or specs specification of each of the cell. That is the libraries. The left layout format, this one. Layout exchange format, that is the left. In .io, input and output files, and library files. Basically, that will store the data of each and every cell in a different, different scenarios, we can say. Okay, what are the scenarios I can say that? Okay, scenarios that your chip has to work in any climate, right? That is like minus 45 degrees. It has to work, and in 100 degrees or 120 degrees, that chip has to work. The maximum threshold is 110 or 120 for each of the chip. At that centigrade also it has to work, right? For that, when your heat is increasing, your performance of chip will be decreasing because of the current loss. And if a chip is very cool, if a chip is minus 45 degrees, let's say, the chip will be super speed. It's how the electrons will behave when the temperature changes. But how the slow, typical, and fast are there. That will be defined according to the PVT conditions. That is the process and voltage and temperature variations. This process is like a fabrication process. How the quality of the process is going on. Okay, and voltage variations due to the heat or a input voltage, and temperature. how the temperatures are being behaving in the outside of the chip. That will be varying for each of the standard cell and their behavior. Okay, so this is all about the data preparation that is required for the backend. So for the layout team. Okay, so next coming to the timing. So what is timing? Someone say what is timing? What is required for this? Okay, the chip will be work at a faster of 5 gigahertz, right? And what is the time period? Someone answer. What is the formula for frequency in terms of time period basically? Frequency equals to 1 by the reciprocal of the time period, right? Okay, when we say 1 second, how much the frequency? 1 hertz, right? That how the frequency is calculated with the time period. When you say it is a speed is increasing, the frequency also increasing, right? And the clock period will also decrease. If the clock period is, you say nanoseconds, in 1 nanosecond, the number of instructions they pass, calculation will happen. That's how the frequency will be calculated. Okay, we'll go into deeper in the next webinar also about the timing, what we call the static timing analysis. Okay, so at the timing preparations, we calculate input to register, from external factors to the register, and input to output path, from input to the output of the chip, and register to register, that is flop to flop timing, and register to output. So these are the scenarios we'll check for a timing. Okay, and we'll apply setup and hold timing calculations. The setup is like the speed, how much the speed which it will conduct. The hold is that the data, how much the data can be weighted for each of the cycle it will take basically. So that's how the setup and hold is calculated. Okay, and there are different stages in the physical design, basically the layout. So coming to the pre-place, we have the pre-CTS, post-CTS, post-step in detail. Okay. First, we comes to the floor planning. What is floor planning? Basically, the floor planning is a step involves identifying the right place for each of the component. It's a component. What are the components? Components are the RAMs, ROMs, analog to digital converters, PLL, which are the clock generators, okay, and any USB connection ports and predefined IPs, intellectual properties like that we call. There's a logic. All this has to be properly placed in a chip. Okay, let's take an example like this. There is a what is it? There is a chip like this. Okay, in this there is a section of RAM. It has to place in the right way. So this will be a RAMs. Okay, all the RAMs has to be placed in the right way so that the other standard cell areas it will be free for the connections. The logic is going from the input output like this. It has to be placed in a proper way. That's how the floor plan will be done. The planning for the each of the modules. Okay. So this is how the floor planning will be done. Next, what is the next process? Okay, next is right. What we are doing is like we were power planning. For each and every standard cell, there are millions and millions of transistors and millions of discretes are there, which are in a layer format. For each and every standard cell, we will be giving a connections like VDD and a ground. Without that, it will work. No, right? So we have to give a connection for each and every standards, or each and every gate, obviously. Okay. So if you say the technology is decreasing, let's say 180 nanometer is very old technology to use input of 1.8 volts. If you say 2 nm, it's just using it 0.2 volts also. Okay. So this is like you're reducing a lot of power and giving a more logic to a chip. And you're also thinking of the design with the technology. Okay. Based on that complexity, how much the power it is using, how much the VDD, VDD or VSS, obviously the power and grounds where connections are using, how much the drop of this voltage is coming out, how much the heat it is producing. So that will be calculated. Okay. All things will be done at a power plan stage. Okay. Next, once the power plan is done, you are doing all the power connections in the layout. What is the next process? Next process is the placement of each and every standard cells. You have placed the RAMs, ROMs, and analog and digital converters. You have created a structure, a power plan, like way that it will connect each of the standards in a pattern. Okay. Once that is done, we'll be placing all the standard cells in a design or gates in a design, in a layout way. It will connect all the connections that are required for the power, and it will ensure that each and every standard cell are placed without any issue. So this is how the placement of standard cells will happen. So once that is done, we will start verifying the timing analysis for setup. Okay, then we are good for the placement. Then after there is a process of placement, there is a main stage is like clock tree synthesis. Okay, why clock trees? Why clock tree? What is clock tree? Clock tree synthesis they call it as. Clock. What is clock? Clock is like the speed. There's for each and every clock there is a clock right input. When clock is high, the activity of clock will high, or it will conduct. Right? So each and every flop in the design will get a clock for functioning or storing of your data. Okay? So that we need to construct this clock tree for each of the flop without any shorts. In a way, we have to wire it or route it properly. Okay. Once we done with the clock tree, we are going to the routing. What is routing? Routing is like you have to connect each and every connection from the gate to gate without any shorts or without any spacing violations. It should have some standard for the spacing to each net side by side. They are properly going, but they don't have any insulation for the side by side wire, right? So we need to use the what is it? Proper spacing and the proper rules and guidelines on the fabrication, on the technology. Okay, whether it is a clock nets or the signal nets or the power nets, we have to ensure with the proper width and length of this wire. Okay, this is how we call it the routing stage. We'll do the routing stage. Okay, so we may see some routing violations like related to the complexity of timing or density of the standard cells. All this comes into a picture. Okay, so once we're done with the routing, so the stage where we check out any violations related to the design rule sets. Like the technology will give the guidelines for each of the net and the wires. If there are any shorts or a wire-to-wire connections, all this will be checked out. Okay, you are good at no violations in your design. There is a zero violations. There is a zero routing issues or in wiring connections. Okay, then you're not seeing a layout versus schematic issues. This is LVS step. What is LVS basically? I'm calling it layout or schematic. And what is schematic? Layout is what we are actually drawing or what actually we are routing in our shape. The same connections, the same way, how the layout is there is same as the schematic or not. What is schematic? Schematic is a Verilog file basically. Whether that is same. There's a two wires. Basically, this is wire is going from here to here. Let me give you some example here. There's a wire going from here to here. The second wire is going from here to here again. And third wire is going here to here. And I see there is no violations here. The connection is very proper. At least second scenario. One wire is going like this. One wire is going like this. One wire is going like this. Now say, is it the correct way? No, right? There's a short here. There's a short here. There's a short here. You even though routed it properly, but these two wires are touching each other, right? So this is called a violations. When you check, this is a violation. VLSI violations are like this is a net, and this is one more net which is going very close, and this is that the spacing violation is not correct. But because of the shorts you see, The schematic is not same as the layout. In schematic, we have the connections like this, but in the layout, the connection is like this. This is failure to the LVS and the complete failure of your chip, right? So we have to take care of each and every net. If your transistor count is in a billion, and your net count will be in 6 billion, because for each gate there the connecting inputs are like in hundreds, that means that 6 or 4. Outputs are 1. Again, it is completely rerouted into double fan outs. The fan out numbers are extra. So like that, the number of the number of connections are more when compared to the transistor numbers. So for that reason, we have a 20 to 25 layers of connections, not in a single layer. In a one floor, we can't route a hundreds of wires, right? So that's where they bring up a hundreds of connections in a one layer. And sorry, hundreds of connections in a layer format. Okay, like M1, M2, M3, and M4. Okay, this is about the DRCs and LVS. What is signal integrity? I'm just talking about, right? When there is a violation, let's take this is a wire. There's no issue with the wire connections. All wires are going like this. Okay, so there is a connection like this. There is a no issue. There is a no spacing issue. There is one more issue here. What is that issue? What is that issue? Issue itself is that this wire is very close, but there is no spacing violation. The violation is that this is too much conductive. This conductivity is too much, so that this net is so weak. Basically, the connection is weak. Let's say there is a wire. You are sending out a connection, like there is a connection. There is a current loss in this net. There is a electrons array, which the movement of electrons will be less when it is started from here because of resistivity of this net or a wire. This net is started disconnecting from here. The boosted is signal is here. This conductivity is more, and this impact will cause this conductivity will cause impact on this other net. That will cause the if input is zero here, that the impact will cause this net to one. The output will change. This is where the crosstalk, the each net impact will cause to other net. That is called conductance basically. Crosstalk. What is called as a signal integrity also. No issues such as crosstalk, noise, electron migration, antenna effects. All these are part of the signal integrity. So we should take that kind of issues when we're analyzing the timing. It may lead also for the functionality of the chip and the speed of the chip. Okay. Let us tape out. All we done with all the process of this chip. We are taking the design completely test out with the functionality and everything, and we are taping out for the fabrication. We are giving out our design to the fabrication unit, that is called as a tape out. Okay, and the file is in a GS2 format currently. Okay, this is not a human readable form. So this file only submitted for the fabrication unit file. Okay, so this is all about the VLSI design flow. And any questions on the bridge? Now coming to the what is the differences between the VLSI and the software jobs? When someone is asking the last call at the post completion of the class, should I go to the software field or some VLSI field? How it is differed? People who are having a EC background, they don't have much interest of coding. Especially the learning course completely for the 4 years or the 2 years in MTech, completely in the EC background, which is EC background. If they are choosing the software, it is different task. The EC is dedicated for the completely core jobs for them. It's all about communications, it's all about electronics, it's all about electrical things. So we have a different growth in the electronics in the current market. The growth of chip is like booming like anything year to year. The requirements for chips and the work which we get is completely innovative and also a success aiming things. Day to day life, you feel like you are innovating in new things. Okay. So every engineer in electronics will work for invent something in everyday life. It's not like a software job can be replaced with some other things like coding. But here this complete picture is different with compared with the real life. Okay. Coming to the salaries. So I was discussing yesterday about the salary things also, right? Or the salary structure for the product companies on the or the salary structures for the software companies. So for the survey-based companies, it ranges from 4 lakhs to 10 lakhs. Okay. For product companies, it will range from 15 to 25 lakhs. And product companies, there is a different process for recruiting. So they will be recruiting for freshers, they will take as an internship and they will serve you for 9 months as an internship. Then they will decide upon your permanent position with the company. Okay. So this is how the VL for the structure for the VLSI for the product companies. Okay. So coming to the what we provide. So currently we are providing the best VLSI courses, training procedures in internship. Okay. The mode of trainings we give, the how the curriculum we design is completely industry standard. So we have the very latest technologies like 7nm, so which is like used for the training purposes, and 2nm and 5nm are very confidential. That is not for the training purposes. Currently, data production with uh, highly they are protected data. So we can't take the data for the training. But 7nm we have with our vendors, which will be using for our designs. Okay, the approach we give for trainings, the training sessions in our. So we give a offline and online modes. Okay, and we have a different tools from the Cadence, Synopsys, and mentor tools from our vendors. Okay. So the other thing that we have a complete real-time projects. We have a 5 to 10 projects. Any training, like basically any PV or DV or RTL, we can say we give all the complete set of trainings here in the site from the ChipXpert. Okay. So in the offline, we are serving from Hyderabad in Madhapur. So anyone can join us this training course. And we have a new batch starting on May 15th. Okay. So the curriculum we decide is completely industry oriented. Okay. And we have a doubt clearing session for every module we complete. And for the offline and online, the complete curriculum is same. And the mode of class custom training is same for online or offline. So people who are in offline mode, right? So they have to connect for this the same session that is going in the online, so offline. Okay. The second thing is that for everyone who training in the VLSI for the ChipXpert from the ChipXpert, we will give a complete tool access till they get placement. Okay. And we'll also provide complete training materials and we'll give a complete recorded access of the training sessions for lifetime access. Okay. So total the training period is 6 months for the physical design and design verification. The 6 months of time will teach you about complete end-to-end flows of VLSI and also the specific domain things. And the first 5 months will teach all the technical things that are required for the specific course. Okay. Okay. Then we'll come to the second level. We'll come to the resume preparation, interview preparation support, which includes we'll teach you the soft skills. We'll ask you to present the presentations among the set of engineers, the training engineers, and also mock sessions, mock interview sessions, and we'll give a complete industry-oriented interview process, how we can attain the interview smoothly. And our industry trainers, basically the industry trainers are having a 15 plus years of experience, and the trainers are having a completely industry-focused training. And you will have a good interaction with our training, and the way they teach are completely industry. Okay? The other thing is that we have a complete hands-on projects. A person can do any of the 5 projects that we have. Okay, this is all about the internship program. Sorry, it is all about the training program. The second thing is that we have internship program for the 45 days for the summer, which is starting on April 5th. I mean, so May 15th. So on May 15th, they're starting internship programs also. This is for the summer internship. We have a 45 days of this internship program, which is in a hybrid model and also in online model. Okay. So this is all about the mode of training with ChipXpert Training Institute. Okay, and the companies which we currently collaborated are Intel, Qualcomm, Cadence, Synopsys, and NVIDIA. There's a mass recruitment gone in the last batch. Okay, anyone interested for this training programs, please contact us. We will also give you discounts who attended this workshop. Okay. Thanks everyone. Anyone having